Welcome to a lesson with Dr. Powell. Let's take a look at del f, or the gradient vector, and we're going to just think about functions of two variables, f, x, y. Okay, in fact, let's take a look at one specifically. Why don't we do x squared plus y squared? Now, for different values of z, this represents a circle of a certain radius. For instance, when z is equal to 4, then it looks like we're drawing a circle of radius 2, but at the height at z equals 4. Okay, so z equals 4 to get up there. And then we have a circle of radius 2 centered about the origin, but kind of raised above the actual xy plane. Now, we can actually, if we wanted to, we could do this. We could draw a picture just in the xy plane, just in the inputs. And we think, okay, when z is equal to 4, we're going to can draw just a circle of radius 2. And we can just put right here, z is equal to 4. When z is equal to 1, actually we have a circle of radius 1. We'd call this z equals 1. Looks almost like a contour map for, like with different altitudes. This is a line that represents an altitude of 1. This is a line that represents an altitude of 4. And if you get this one, this would be the one at z equals 9. Then you'd have a circle of radius 3. Okay, so these contour lines are called level curves, because they're a projection of the actual curve at a certain level, or the surface being cut at a certain level. At a certain level, that's kind of what, when z is equal to 9, then you would see, that's what you would see, that crosscut of the surface. So you can kind of get a visual for what the surface is going to look like if you just look in the xy plane where all the inputs are. Okay, now something interesting. Let's talk about how the gradient pops in and how it interacts with these level curves. Well, it's true that if you're moving along, what happens if you move right in the direction? What if your input, the change of input, is right on one of these curves, or kind of in the direction tangent to one of these curves? Well, then you can expect that the z value won't be changing. It'll be staying at the same height. But what happens if you go this way? Going up this way, perpendicular to that, you actually can expect to grow a lot. In fact, let's kind of think about that idea for a minute. Fx, Fy as a vector can be thought of as the derivative. And if we dot it to, or if we think of it now let's think of it as a matrix though. Because let's try to compute the idea of rise given a certain input. What if given a certain run? So what if our run was tangent to the level curve here? Tangent to the level curve. So I'll just make something up like u1 and u2. Suppose that this right here represents a vector u1 comma u2, which is tangent at some point to the level curve. Then you can expect, since you're saying tangent on it, so you're kind of staying on the level curve, the z value, the height isn't changing. So the rise, you can expect the rise to be 0. So you can expect this dot product to be 0. But what does dot product 0 mean? Dot product equals 0 means perpendicular. So that actually tells you that the gradient is perpendicular to the level curve. So the direction right here that we're traveling is actually in line in the same direction as the gradient, fx, fy. I guess we could just label it as del f. So we're going to be using that too later in order to solve different types of problems, kind of a fun fact, that if you have a level curve, if you have your level curves for whatever your surface is, your derivative thought of as a vector, as a gradient vector, is always going to be perpendicular in the plane to your level curve. Thanks for watching.